Hi students, welcome to the second part of this video. In this reaction we take the benzene and react with the H2SO4, and we don't need a catalyst here because the sulfuric acid acts as the order catalyst. And what you get, we replace here the hydrogen as H plus ion, okay, correct, with the sulfonation, right? So we don't need a catalyst actually. And what actually we get the from this ring you get the benzene and you get the SO3H, right? This is the compound that we get, correct? Plus you also get the water there, right? This is the reaction, okay? So electrophile, now if you look at the reaction again, it looks like the the electrophile from the H2SO4 is SO3H, correct? Looks like that the electrophile that you get from the H2SO4 is SO3H, or you can say HSO3, right? And that replaces the hydrogen because you get the SO3 here, SO3H here, correct? Okay, it looks like that, but very interesting, the electrophile that we get from the H2SO4, the electrophile that attacks on the benzene ring is not this one, rather the electrophile is SO3, and this is the neutral SO3, which releases the hydrogen from there and forms then SO3H. So the electrophile, right, very interesting, the electrophile that we get from the sulfonation is SO3, neutral molecule, sulfur trioxide. Sulfur trioxide neutral molecule acts as a this electrophile, and it is this electrophile which attacks on the benzene ring. Initially we have, in the previous two examples, in the halogenation we discussed that the electrophile is Cl positive. In the nitration we discussed that the electrophile is NO2 plus, but right now in the sulfonation it's not SO3 plus, right? It's not SO3 plus or like that, rather the electrophile is SO3. The sulfur trioxide, neutral sulfur trioxide molecule is electrophile because SO3, we have in the previous if in one of our videos, if you go back to the electrophiles and the nucleophiles, we have discussed that some of the nucleophiles and the electrophiles are neutral as well, correct? So a neutral molecule can also act as electrophile. Sulfur trioxide is one of them, okay, because sulfur trioxide is a neutral molecule which acts as electrophile. It's an electron deficient molecule. Why it is so? Let's discuss that first, and then we'll go to the mechanism. Sulfur trioxide is like this, okay? It has a triple bond, correct? So we can argue the 2 points there, in favor of sulfur trioxide. Why it acts as an electrophile? Why it acts as electron deficient? Number one, it has 3 different electron withdrawing groups attached. Delta negative, and delta negative here, right, and delta negative over here also. Then the sulfur will get a sufficient amount of a positive charge, so electron deficient, right? The second point, because of the resonance in the sulfur trioxide, okay, because of the resonance in the sulfur trioxide, it acquires a resonating structure like this. Sulfur O negative there, a double bond is here, and the sulfur has a positive charge. So because of the resonance, right, the electron pair, the pi bond shifts towards the oxygen. So it again, so that means both the structures contribute that the sulfur is electron deficient, and therefore now you have an electron deficient center in the sulfur trioxide. Therefore sulfur trioxide can act as electrophile. Now let's come to our main topic here, that is sulfonation, right? So from H2SO4, basically the electrophile that we get is sulfur trioxide, and it is this sulfur trioxide which attacks on the benzene ring. Now let us discuss about the mechanism of a sulfonation, right? The first step in the sulfonation, right, is actually the formation of electrophile, and that electrophile is generated from the H2SO4, and H2SO4 is the order catalyst, right? So H2SO4 is the order catalyst, and let's see how the sulfuric the sulfur trioxide SO3 molecule, right, because SO3 neutral molecule is actually has to be generated from the H2SO4. So sulfuric acid is like this, okay, it has a structure like this. So in this molecule, the same proton, right, H plus, attacks on the oxygen of another molecule of the same molecule, right? So you can see like this, and it forms the it undergoes the protonation there. O negative there, OH, and H is here, right? So you get a positive charge on the oxygen when it forms a bond over here, correct? And then the sulfur, this electron pair comes off with oxygen, and you get the water, H2O, but the sulfur trioxide you also get, right? O negative plus, right? Then it goes down and undergoes the resonating structure where you have a SO3. These are the two resonating structures of the SO3 molecule. Now this is the electrophile, right? This is the electrophile that attacks on the ring. Then the second step is on the benzene ring, okay? On the benzene ring, the same molecule will attack. The sulfur trioxide will attack. See, we have a hydrogen over here, the sulfur, right, with a double bond here, and see, this is the oxygen O negative and the sulfur positive charge, and this electron pair forms the bond with the sulfur trioxide, and what you get? You get an intermediate like this. Okay, you have a sulfur now, then O negative here, and H is there, okay, double bond O and double bond O. And the same thing like in the previous example, the hydrogen comes off as H plus, okay, that attacks on the same oxygen here. Very interesting, on the oxygen with O negative, and what you get? You get this molecule, you get the benzene, and this electron pair goes inside the ring, it forms a double bond there, and now you have a sulfur, double bonded O, and the OH. And this is how we write it like this, right? Okay, this is how we write it, like the benzene ring with SO3H. So something is special in this reaction, right? The attacking molecule is SO3, but the final group that you see here is SO3, right? However, the electrophile is SO3. Is that clear? So this is the mechanism. You know, the first step is attack of electrophile. So first step is the generation of electrophile SO3. This is how actually you get the SO3, and then the SO3 molecule attacks on the benzene ring. You get intermediate. The hydrogen which is lost actually from the benzene ring, right? This is something special here. The hydrogen which is lost from the benzene ring, actually it goes to the oxygen, and you get the HSO3, correct? So if I write it like if you write the reaction like this, the overall reaction I can write it like this, right? So overall reaction is that you have, suppose, a hydrogen here, okay, from the benzene ring, and this hydrogen, when it interacts with the H2SO4, okay, what do you get? You get the benzene ring with the SO3H, okay, plus you get the water. Let me use a slight color coding because that will actually help us to understand it a little bit better. So the hydrogen which was actually attached with the benzene ring here, okay, the hydrogen that was attached to the benzene ring, it is the same hydrogen that we find with the final group. It's not the hydrogen from the sulfuric acid, right, which you find here. It's the hydrogen from the benzene ring that goes to this one, right, in the sulfonation. That's why initially I said that this is a little bit different one, correct? Okay, so see, that means if you have a deuterium here, right, if you have a deuterium here or tritium here, okay, the isotope of the hydrogen, then you can find the SO3D like that, not the H2SO4, because these two hydrogen atoms they go with the water. Clear? Okay, so this is the sulfonation, correct? This is the electrophilic aromatic substitution reaction. This is the third reaction that we have discussed. Now the other two reactions are Friedelcrafts alkylation, correct? The Friedelcrafts alkylation. Alkylation means if you attach an alkyl group, right? So here the electrophile should be the R positive, okay? The R positive is the electrophile that we find, and in the alkylation what we do, suppose you take the chlorobenzene, you take the benzene and react it with the, suppose, any alkyl halide, okay? any alkyl halide, and we use also a catalyst, the Lewis acid here, the AlCl3 for example, and what you get, the R positive, which is generated from this one, attacks on the benzene ring and it replaces the hydrogen from there, and you get the alkyl benzene. Okay, you get the benzene ring there with the R group, plus you get HCl. Again, now let's discuss its mechanism. Correct? What is the mechanism? I think the mechanism is almost the same. Steps will be the same. The mechanism. Okay, the first step is always the formation of electrophile, right? As in the last three reactions, here also the same. We have to generate the electrophile. Correct? So the R positive has to be generated from the alkyl halide. Let's take an example here of suppose we have we have ethyl chloride, C2H5Cl. Okay, if I react it with the, when this ethyl chloride reacts with the AlCl3, okay, with AlCl3 we know that it helps to generate electrophile. It forms the chlorine, forms the bond with the aluminium because it's a Lewis acid. It has a low number of electrons, right? It can form a bond, and then finally the chlorine carbon bond breaks, and you get what? You get the CH3 CH2 positive, right? The alkyl group you get, plus you get the AlCl4 negative, right? You get the AlCl4 negative. This is the electrophile that we need, and it is the same electrophile which attacks on the benzene ring, and this mechanism is same. Correct? So I'll write down here only the final reaction, right? So the final reaction we'll discuss only. Suppose the mechanism we have discussed, right? So now you have a CH2 CH3 here. This is the electrophile. Okay, forms the bond here with this one. Correct? And what you get? Say you get final product. I'll write down when the hydrogen comes off, right? The mechanism in the second step is same, right? The mechanism is same like we discussed in the first first three reactions, right? An attack of electrophile, you get intermediate, you get a carbocation here, then the hydrogen comes out. Okay, hydrogen comes off as H plus ion. Okay, and then you get the intermediate. Now, and then the third step is that in the third step the AlCl4 negative, right? AlCl4 negative that reacts with the H plus ion here, and you get the HCl plus AlCl3. This is the mechanism of reaction. This is called alkylation. But see, the problem with the alkylation is that we know that the intermediate that we get here is the carbocation, correct? So we know the intermediate in the alkylation is that is the carbocation, and carbocations have a property, right? A very important property, that they undergo rearrangement. If there is possibility that they can undergo the rearrangements, correct? So carbocations can undergo the rearrangement. That means if you have a 1 degree carbocation, it can rearrange to the secondary carbocation. Suppose in a particular reaction, correct? Suppose if I take a benzene ring and I react it with a molecule like this. If I reacted this molecule with the CH3 CH2 CH2 Cl, right, in presence of AlCl3. Now there are different types of products actually which are possible, right? So there's not only one product that I can predict. I can say that the chlorine is lost here and the CH3 CH2 CH2, this is the alkyl group that attacks on this one. But rather than one product, in this reaction you find two products, correct? I find the two products. Now let's see what are the two products possible. Okay, first look at this one. The first step is that AlCl3, it will form a bond with the chlorine, and the intermediate that you can expect from here will be CH3 CH2 CH2 plus in the first step of the mechanism, right? So the intermediate is actually what? CH3 CH2, if I write it like this. Okay, this is the intermediate, CH3 CH2 plus, and you can say that okay, this electrophile will attack on the benzene ring, correct? But in this carbocation, if you look at this carbocation, this is a 1 degree carbocation. The carbocations can undergo rearrangement. Okay, so this particular carbocation can undergo rearrangement. Okay, so how is that rearrangement possible? The hydrogen with electron pairs, it will shift over here. Okay, and then you can get a secondary carbocation. You get a carbon with positive charge on the second carbon over here, and what you get? You get the C, H, H and H. This is called as the rearrangement, right? And the rearrangement of the carbocation, from 1 degree it changes to secondary. Secondary is more stable, right? That's why the rearrangement occurs. the driving force for the carbocation rearrangement is that the stability, isn't it? The secondary is more stable, so therefore the primary can rearrange to the secondary, but the reverse is not actually possible, correct? If you suppose in a reaction you get a secondary carbocation, it cannot go back to the first one, so rearrangement is always in the increasing order of the stability, correct? So here this rearrangement is actually possible. So when you start the reaction with the propyl chloride and the benzene, you get the first carbocation, but there is also the possibility of rearrangement, right? So some of the molecules can rearrange and they form the secondary carbocation, and this rearrangement is possible by hydride transfer, right? We call it as a hydride transfer. Okay, this is the hydride transfer. So H negative, right? H negative, hydrogen with electron pair. This is not H plus, rather this is H negative. So hydride transfer actually occurs from this carbon to this carbon, right? So both electrons they shift here and you get a secondary carbocation, correct? This is more stable carbocation. And now in the reaction, in the reaction mixture actually you have both the carbocations 1 degree as well as the secondary carbocations, correct? And then when this 1 degree carbocation attacks on the benzene ring, what you expect? If you suppose if you have a benzene and it replaces the hydrogen from there, right? What do you get? You'll get the product like this: CH3, CH2, CH2, and the benzene ring. So this is the propyl group here attached to this one. But from here, when the secondary carbocation attacks on the benzene ring, the product will be like this. Okay, the product will be CH3, CH, benzene ring here, and then the CH3. Okay, and this is the major product, right? This is the major product. This will be the minor product. This will be formed in a lesser quantity, lesser proportion, right? Why? Because the secondary is more stable, correct? So in the reaction mixture you will see that the reaction mixture that contains more secondary than than the primary. That's why with the alkylation different products are possible, correct? So here you find the two types of products possible. Why? The reason is because carbocations can undergo the rearrangement. Okay, that is the very common reaction of the carbocations. And the second reaction similar to this one is Friedelcrafts acylation, right? In the Friedelcrafts acylation, we know the acyl group is attached, correct? Acyl is like this, RCO. This is an acyl group. Okay, and the electrophile that we need in the acylation is RCO positive, right? This is the electrophile that we need. Okay, and it is this electrophile which replaces the hydrogen from the ring, and then it forms what? It can form the benzene ring attached with the acyl group also, C11OR. Okay, so the reagents we use, we have different kinds of reagents. One of them is acid chloride, right? One of the most common is acid chlorides. So with the acid chlorides, again we can use the acid, the AlCl3, the Lewis acids here. Again the same thing happens here also, right? You also get the HCl. This is the reaction. The AlCl3, it replaces the chlorine as the Cl positive, as the Cl negative there from this one, and what you get? RCO positive, AlCl3, right? If you look at the mechanism, right, let's discuss the mechanism of this particular reaction, how the reaction actually occurs here, right? So in this reaction, the first step is, if we write down the mechanism of this reaction, right, the first step again the same, the attack, the generation of electrophile. We have to generate the electrophile, correct? So we have to generate the electrophile. Okay, the electrophile here is RCO positive. We need this electrophile, correct? And for that we use acid chlorides. Okay, acid chlorides. We can also use the anhydrides also. So I'll explain here with the acid chloride. This is the acid derivative actually, RCOH. Okay, so if you replace the OH by the Cl, this is the acid chloride. And if I react it with the AlCl3, we know that AlCl3 is a Lewis acid, and it can form a bond with the chlorine atom, and the chlorine will come off finally, and what you get? You get AlCl4 negative, right? You get AlCl4 negative plus, once the chlorine comes off from here, you get the RC double bond O positive, acyl chloride. Okay, sorry, this is the acyl group. Okay, so acyl carbocation, correct? So this is the electrophile that we need in the acylation. Okay, and then the same the RCO positive attacks on the benzene ring over here, and you get this one. This the same CO positive, right? RCO positive attacks on the benzene ring, replaces the hydrogen there, and you get this compound and form the HCl, right? Hope you understood the concept. Thanks for watching the video. Bye.